Probably. All right, how's it going? What's on your mind? It's Friday. It is Friday. It's the last Friday of class. When does all, I mean, I wrote it in Canvas. When's your final for 17C? Tuesday, okay. All right. Well, we'll be, so starting Friday, we'll have office hours and drop in. Me, Grant, Ryan, Jen, probably. What else? Let's see what else. All right. I heard you guys talking about some union stuff, intersection stuff. Okay.
Covered like probability.
Right.
I think he briefly mentioned like exclusivity. Like
Okay, sure. Yeah, we can get to that. We're gonna get to that anyway. So. Conditional probability, yeah. I mean, there's not a whole lot more to say after conditional probability other than talking about Bayes' formula. Probably, yeah. We can probably get there today. Yeah. Where am I? One moment. Not you. Go away. Lots of pieces of paper.
oh, the song.
All right, so let's look at some probability stuff. We'll start with a couple of examples. Probability. So let's look at this example. And I think we maybe talked about this example before, but we didn't quite talk about the probability stuff. So we're going to say a fair coin is flipped 4 times. Or alternatively, you flip 4 coins. We're just going to start off by listing the sample space. And the sample space is just everything that can possibly happen. So list the sample space. It's usually denoted by the Greek letter omega. So in this case, omega is going to consist of these 16 different things. How do I know there's 16? Well, we'll talk about that in a minute. But I know I can either have all heads, and we did do this before, or you can have 3 heads and 1 tail, and there's 4 ways you can get that. You can have 3 heads, then a tail, or a heads, heads, tails, heads, or a heads, tails, heads, heads, or a tails, heads, heads, heads. We were talking about this before because we talked about how there's exactly 4 ways of getting 4 heads. And there's 3 ways of getting 3 heads. And if we talk about 2 heads, we can do heads, heads, tails, tails, or heads, tails, heads, tails, or heads, tails, tails, heads, or tails, heads, heads, tails, tails, heads, tails, heads, tails, tails, heads, heads. And there's exactly 4 choose 2, which is equal to 6 ways of doing that. And lastly, these are just going to reflect. So instead of having all these, we're going to have tails, 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 heads, tails, tails, heads, tails. I'm just interchanging all the tails and heads from this column here. Tails, heads, tails, tails, and heads, tails, tails, tails. Again, 4 choose 1 heads is equal to 4. And lastly, all tails. I know, it's not exciting. 4 choose 0 heads is still one way of getting that. So that's the sample space. All the possible things that can happen when we flip 4 coins. We could use some notation to say the number of elements in the sample space, n of omega, is, well, normally you wouldn't just add, like, you wouldn't normally just list them out and count them up, right? We could 1 plus 4 plus 6 plus 4 plus 1 is 16. But really, this is where we should think about how to count the number of things that can happen. So if we flip 4 coins, how many possible things can happen when we flip the first coin? We can either get, so there's 2 possible outcomes. And then for the next coin, there's 2 possible outcomes. And then for the third coin, there's 2 possible outcomes. And for the fourth coin, there's 2 possible outcomes. And 2 times 2 times 2 times 2 is 16. Great. So we totally knew how many things could happen before we even wrote them down. So then we can start naming things, like we can say, let's say that A, capital A, is the event. We typically phrase things as events of flipping 2 heads. What's the probability of A? Well, the notation for this is capital P parentheses your event, A. So the probability of A is how we write that, or how we say that, and that's how we write it. And the probability of A is exactly what we talked about before. The number of ways the thing can happen divided by the total number of ways anything can happen. So it's going to be the number of ways that we can flip 2 heads divided by the number of ways of anything in our sample space happening. In this case, that's going to be 6 out of 16, which reduces to 3 over 8. Because we listed them out, right? Right up here, there's exactly 6 different ways. So right here, this is event A essentially, right? Flipping 2 heads, there's 6 different ways you can flip 2 heads. Without listing them out? Well, yeah, by using the binomial coefficient. So if you didn't want to list out the 6 ways of flipping 2 heads, you could have said, oh, I know if there's 4 coins I'm flipping and I want 2 of them to be heads, there's 4 choose 2 ways of making that happen. Either, I'm going to say them all, the first 2, the first and the third, the first and the fourth, the second and the third, the second and the fourth, or the third and the fourth. Those are the 6 different ways the 4 choose 2 ways of picking 2 of those 4 coins to be heads. So in fact, I'll expand on that in a minute because this problem is small enough barely that you can write them all out without too much problems. But if you did 5 coins, that's 32 things. And that kind of gets to be a little bit unwieldy. Let's look at a few more questions here and then we'll kind of talk about that. So let's say that capital B is the event of flipping either 3 heads or 4 heads. The probability of B is going to be, well, since these events are mutually exclusive, which means there's no overlap between them. You can't have the event, it's not possible to flip 3 heads and 4 heads at the same time. At least not exactly, I should say, exactly 3 heads means 3 heads and 1 tail. If I had used the words at least 3 heads, well, that would actually be what I'm calculating right now, getting 3 heads or 4 heads. So since these events are mutually exclusive, we can say the probability of B happening is the probability of 3 heads plus the probability of 4 heads, and that's just going to be, well, the probability of getting 3 heads was 4 out of 16. The probability of getting 4 heads was 1 out of 16. That's going to be 5 out of 16. Okay, let's look at another thing here. Let's say that C is the event of flipping at least 1 head. And we've talked a little bit about this idea before, but we're going to say it again. So one way we could do this is say, well, the probability of C is just going to be the probability of one head plus the probability of two heads plus the probability of three heads plus the probability of four heads, which is going to equal, let's see, the probability of one head was, I forgot, there's four ways of getting one head, I think. Yes, so it's going to be 4 out of 16 plus 6 out of 16 plus three heads is four ways out of 16 ways plus four heads is one way out of 16 ways. And if you add that up, you get 15 out of 16. Or we could use what's called the complement. So instead of counting up all the ways of getting at least one head, count up all the ways of not getting at least one head. Well, if I want everything else, the only other thing that's left is getting zero heads. So you could say the probability of C, which is getting at least one head, is equal to 1 minus the probability of D, where I haven't told you what D is yet, where D is getting no heads or zero heads. Well, the probability of getting zero heads is, well, let's see, there's only one way of getting zero heads, all tails. So that's 1 out of 16. And 1 minus 1 over 16 is 15 over 16. This idea happens a lot, where instead of counting up like all the ways of getting at least one, so one or two or three or four or whatever, you instead say, oh, I'm going to say it's the total probability of anything happening is 100%. Right? There's a 100% probability that one of these five things is going to happen. You're either going to get four heads or three heads or two heads or one head or zero heads. You flip four coins. So take that 100% probability and subtract the probability of the stuff that you don't want to happen to get the probability of the stuff that you did want to happen. See, is there anything else I want to say about that? Let's look at yeah, sure. Let's look at some more examples here. Also, if you have questions along the way, you're more than welcome and encouraged to ask them. But let's talk about this next example, which is, sure, that was number one. This is number two. So typically when we're flipping coins or rolling dice, we assume they are fair, meaning there's an equal likelihood of any one of the number of possibilities coming up. Right? If you're flipping a coin, we assume it's a 50-50 probability. If you're rolling a six-sided die, we assume each side has a 1/6 probability of showing up. So we roll a fair six-sided die, which has the possible outcomes: a 1, a 2, a 3, a 4, a 5, or a 6. It might look kind of like this. And you can't see the other three sides. And let's say that we have the following. We're going to let A be the event of an even number being rolled. So A is the set containing the possible outcomes 2, 4, and 6. And I should have called this up here omega, by the way. This is omega, the set of all possible outcomes. And then we're going to say that B, let B be the event, that sounds terrible, of a multiple of 3 being rolled. So B is the set consisting of the outcomes 3 and 6. So we're going to find two probabilities, but before we do that, oftentimes when you have sort of these different events and they might overlap, it's very useful to draw a Venn diagram. So we typically draw a big rectangle, and that's our entire sample space. So everything has to live inside here. And then we draw circles to represent the different events. So there's A and there's B, and there might be some overlap. So let's see. So inside A are 2, 4, and 6. Inside B are 3 and 6. So 6 should be in the intersection of A and B, or the overlap. And then A also has 2 and 4. B also has 3. And then not contained in either of those are 1 and 5. we can calculate some probabilities really straightforwardly here. The probability of A, well, it's the number of things in A divided by the number of things in our sample space, which is just going to be 3 out of 6, which is 1/2. I will say I'm being probably writing more than you would need to, right? If you were finding the probability of A, you'd just be like, it's 3 out of 6, which is 1/2. Similarly, the probability of B, we should just say it's 2 out of 6, which is 1/3. The probability of A intersect B, the overlap, is going to be, well, just looking at it, we can see it's going to be 1 out of 6. There's one thing in the intersection, it's 6, and there's 6 things in the total thing. Now, do I want to say that yet? Not quite yet. There's also the probability of A union B. So I should just say more down here for a moment. A intersect B is the intersection or overlap of A and B. In other words, an element has to be in both sets to be in the intersection. In this case, 6. An element needs to be in both A and B to belong to the intersection A intersect B. On the other hand, the union is the set containing anything that is in either A or B or the overlap. So A union B is all the things, all the elements, I guess to be more mathematically quick, in either A or B. So something really, 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 really important about the word or here. This is the mathematical or. It's different than the usual English language or. If I am at dinner and the waiter asks me if I want soup or salad, both is not an option. In math, that's not true. In math, when I say A or B, it also could be both of them, right? If I say I want to be in set A or in set B, it's also okay to be in both sets at the same time. You're still satisfying that requirement. So the other one, the one that we usually think of in the English language, the or for the super salad, that's called an exclusive or. You exclusively get one or the other and not both. Whereas in math, typically we have what's called an inclusive or. You get one or the other or both. So here, I didn't write it, but we say or both. So here, the probability of A union B, in fact, here's the formula for it. It's the probability of A plus the probability of B. But if we calculate, so we're not finished there. There's still more to say. But I just want to point out, if we do probability of A plus probability of B, we're going to overcount. We're going to double count the intersection, right? You're going to get 2, 6, and 4 counted, also 3 and 6 counted again. So since we're double counting the overlap, we're going to subtract it once to make sure that we are accurately counting all the things we actually want. We know what the answer should be already, right? If you look at A union B, how many things are in there? 4. And so our probability should, right? There's 1, 2, 3, 4 things in A and B, or A or B, I should say. So our probability shouldn't be 4 out of 6. We calculate this, the probability of A is 3 out of 6. The probability of B is 2 out of 6. And oh yeah, look, we're over counting, so we better subtract by the probability of the intersection, which is 1 over 6, which ends up being 4 over 6, which is 2/3. So this is the typical formula for the union of A and B. It's the probability of A plus the probability of B minus the probability of the intersection. I will also point out you could flip this equation around and isolate the probability of the intersection. Although it's not typically done, you could say the probability of A intersect B is equal to the probability of A plus the probability of B. Yeah, that's right. Minus the probability of A union B. But we don't usually. But you could, right? I'm just taking that equation and I'm subtracting this over there and adding that over there. Some other language things. When I think about an intersection, we usually use the word and. So if I want to find the probability of being A intersect B, I'm really saying I want to be in A and in B. Whereas if we say a union, we usually think of the word or, the inclusive or. I want to be in A or B or both. The or both is always implied, unless it is specifically said to not be implied. In this class, I don't think we ever talk about an exclusive or, so you're good to go. Sure. Let's look at one more thing here. I wish I had just a little bit more room, but we'll talk about what's the probability, and yeah, we can still see that. So what's the probability of a, sure, union? I'm going to say just five is rolling a five. Well, again, I'm just going to use the formula for the union. It's the probability of A plus the probability of rolling a five minus the probability of A intersect five, meaning event A happening and rolling a five happening. And again, the probability of A is just 3 out of 6. The probability of rolling any single number is 1 out of 6. And A intersect 5, or the overlap of the set A and the rolling of 5. Well, if we look back at our Venn diagram here, they don't overlap. You can't roll a 5 and have event A happen. You can't roll a 5 and roll an even number in the same roll, right? It's literally not possible. So this here, this is equal to 0 because that set there, A intersect 5, is empty. There's nothing in it. Those events are mutually exclusive. If one happens, the other one absolutely cannot, and vice versa. So that's what we say when we say that things are mutually exclusive. It means if one is happening, the other definitely cannot be happening, and vice versa. So anything else I want to say about that? Yeah. So I just want to say that A and 5 are mutually exclusive events. Another word used for this is that they are disjoint. But the way I would always think of it is there is no overlap. Question so far? My question so far. Where's my block? There it is. Let's see, sure. So let's look at a few more examples and then we'll start talking about conditional probability because that's where things really get interesting. So let's look at the following thing. Why am I looking at I've got my notes right here. I'm looking at my computer as well. But it's fine. Sure. So let's look at this. Typical deck of cards. It's three. Yeah, three. Usual deck of cards. How many cards? 52. Okay. So one card is chosen. The chosen one. Find the probability that the one card we drew is, question A, an ace or a face, which means an ace card or a face card. Okay, well, an ace, there's 4 of those. And face cards are the jacks, queens, and kings. 4 jacks, 4 queens, 4 kings. So there's 12 face cards. So if I call this being an ace event A and being a face event F, the probability of A union F is the probability of A plus the probability of F minus the probability of the intersection. However, we know that being an ace or being a face, those are mutually exclusive. You cannot be an ace and a king at the same time, at least not in the deck of cards. So this formula reduces down to just the usual the probability of the intersection, sorry, the probability of the union, apologies, is just the probabilities added together if they are mutually exclusive, which they are in this case. So in this case, it's just going to end up being the probability of A, which is 4 out of 52, plus the probability of F, which is 12 out of 52, which is 16 out of 52, which reduces to 4 out of 13. What if I wanted to get a club or a jack? Why don't you all try writing this? Try the words. Why don't you try writing this one down? So let's say you want to find the probability of a club or a jack. That's going to be the probability of a club plus the probability of a jack minus the probability of the intersection, where the card is a club and a jack, which is possible. All right. How many clubs are in this deck of cards? Right. How many jacks? Right. So the probability of a club is 13 out of 52. The probability of a jack is 4 out of 52. The probability of a club and a jack is 1 out of 52. There's one card, the jack of clubs. That is a jack and a club. And so that's going to be 13 plus 4 minus 1. So that's going to be 16 out of 52, which is equal to 4 out of 13. Coincidentally, the same probability as the previous thing, although not really for any good reason, other than there happen to be exactly 16 cards that are clubs or jacks, and there's happen to be 16 cards that are aces, kings, queens, or jacks as well. Interesting. And it's kind of, if you think about it, right, there's so I should have brought the paper with me as well. So when I'm thinking about this deck of cards, I'm kind of thinking about them like, here's my ace two all the way through king of jet of, diamonds, my ace two all the way through king of clubs, my ace two all the way through king of hearts, and my ace two all the way through king of spades. And so when I'm looking for how many clubs there are, well, there's 13 clubs. I'm looking for how many jacks there are. Well, there's 4 jacks. But then one of those jacks overlaps with one of those clubs. So the 13 plus the 4, and then we subtract 1 gives us the 16 things that we're finding. It's kind of a nice visual. Let's see, let me go back over here for a second. Sure, let's look at that. This one always feels silly, but I do feel like it's worth mentioning. So what's the probability of getting a red card or a black card? In case you didn't know, the red ones are the hearts and the diamonds, the black ones are the clubs and the spades. So, well, let's say that A is getting a red one, B is getting a black one. The probability of A or B, or A union B, is the probability of A plus the probability of B minus the probability of the intersection. Okay, what's the probability of getting a red card? Right. You can say 26 out of 52. You can also say 1/2. Right. I know for a lot of these, I haven't reduced the fractions because I knew I was going to have to do some addition or subtraction before, so I didn't. Here it's okay because it's going to work out just fine. What's the probability of getting a black card? What's the probability of getting a card that is red and black? 0. There are 0 such cards. So, not surprisingly, the probability of getting a red or black card is 1 or 100%. If you pick a card, it's going to be red or black. You have no option, right? It's going to happen regardless of whichever card you pick. There's a 100% probability that it's going to be either red or black. Okay, let's look at, sure. Two more card questions, and then we'll move on to conditional probability stuff, which is a little bit more interesting. So let's say now we're dealing with typical poker hands. So I want to know if five cards are dealt from a deck of 52, what is the probability of getting all five being hearts? We talked a little bit about this last time. So again, the probability, and let's say that, let's call this event A. We typically label events with A and B and C. The probability of event A happening is the number of ways of that event happening divided by the number of things in your sample space. Here, the number of things that are in our sample space are all the different possible five card hands you could get. So all the different ways you could get five cards out of 52 cards, which is going to be 52 choose five, which is a big number. I don't know what it is exactly, but it's large. Oh, I know what it was like. Yeah. So that reminds me of something though. In case you're curious, see if let me look and see. Does this calculator have that button? Some calculators do have a button for this function. It usually looks like something like NCR or NCK. That's N choose R. So I feel like it's on this calculator somewhere, but I do not see it, which is too bad because it's, oh, you know what? I think it's in the stat section. Let's see. Nope, not in the stat. Maybe it's in the probability section. You think maybe? Yeah, it's in the probability section. There it is right there. It also does the permutations one. So, but if I wanted to find 52 choose 5, I actually need to have written 52 first. So let's do 52 and then probability and then NCR and then 5. You don't need to write this down in this problem, but I just wanted to show you it is there. It's big, right? It's 2,598,960. There's a lot of different poker hands you could get, or a lot of different five card hands you could get. On the other hand, the number of ways of getting five hearts, well, how many hearts are there? 13. How many do we want? Any five of them. So that's our answer. 13 choose 5 over 52 choose 5. You should not simplify this or reduce it or do anything. You should just leave it like this. Okay, slightly different question. What's the probability of getting a flush? Let's call that event F. Well, to get a flush, it doesn't have to be all hearts. It could be all clubs or all spades or all diamonds. So instead of being just 13 choose 5, it's really going to be, well, it's still going to be 52 choose 5 on the bottom. And then before up here, we didn't have to do the step of picking a suit because it was already chosen for us. They said hearts. But now, before we say we want 5 of this kind of suit, we have to pick which suit we want. And there's exactly 4 choose 1 ways of picking the suit. Clubs, diamonds, hearts, or spades. And then we multiply that by 13 choose 5. The number of ways of picking 5 of whatever suit we happen to have decided upon. So there's 4 times as many ways of getting a flush as there are of getting a flush with hearts in it, which seems reasonable. Okay. Sure. I guess we should do that. No, I don't want to do that. Well, maybe we'll come back to that. Let's talk about conditional probability because we have not a lot of time left, and I think we should talk about that before the end of the class today. So let's move along to conditional probability. So let's look at some examples. Yeah, let's look at this example. So we're going to draw two cards from a deck. I know, still cards. Cards are easy examples to come up with. Find the probability that the first card is a heart given, oh, sorry, nope, not given yet, apologies. And the second card is a heart. So this is not conditional probability yet. This is still leading up to that. Okay, so A is the first card is a heart. B is this, that's a B, by the way, is the second card is a heart. So the probability of A and B, well, it's going to be the probability of A times the probability of B. Oh, I feel like there's something. Yeah. I keep making little mistakes here. Let me add a caveat here. Sorry. So part A, the caveat is with replacement, meaning that before you draw the second card, you replace the deck with the first card you drew. This one's easy to find. This is why we're doing it first. So what's the probability that the first card to pull from the deck is a heart? Well, it's 13 out of 52. And then I put that card back in the deck. I pull another card from the deck, like shuffle them up, pull another card or whatever. And now what's the probability that the next card is a heart? Well, it's still 13 out of 52 because it's still the same probability. So in this case, it's just 13 out of 52 times 13 out of 52, which ends up being 1/16th. And we just multiply those probabilities together. Now, it's more interesting to ask this question without replacement. But we're kind of used to doing this, right? We know that to find these probability, well, we're going to do it the normal way first, and then we'll talk about what this actually means. So, what's the probability that the first card I drew off the deck was a heart? Right, still 13 out of 52. But now we've removed that heart from the deck, right? We're holding it in our hand. What's the probability the next card is a heart? 12 out of 51, right? We've removed the card from the deck. So the number of things we're drawing from is also smaller. Okay, so this probability, the probability of A and B both happening, here's how we'd write this probability. It's the probability of A multiplied by, instead of the probability of B, that's actually the probability of B given that A already happened. Typically, yes. I don't ever, I try to avoid saying always because there's usually an exception. So here we could simplify this if we wanted to. This is 1/4 times what? Let's see, 1/4 times 12 over 51. The 12 reduces to 3. That's 3 over 51. That's 1 over 17. So slightly less likely to happen, right? If you replace the card, you have more of a chance of both of them being hearts than if you don't replace the card. So let's talk about this conditional probability formula. So there's 3 different ways of thinking of it. I'm going to tell you the way that I think is the best. I'm going to tell you all of them. I'm going to tell you which one I think is the best. So the probability of B given A is equal to the probability of B, now I'm about to say it wrong, B and A divided by the probability of A. This is my preferred way of writing this formula. I feel like it makes the most sense. You're saying essentially, in fact, let me draw a picture for you. If we've got a Venn diagram thing going on, here's A, here's B. So if I'm trying to find the probability that B happens, given that A already happened, well, I'm trying to say, I'm basically saying this circle here, that circle of A is our entire world. As far as we're concerned, in this moment, if we're trying to find the probability of B, given that A already happened, well, cool. We are reduced down to just saying A's already happened. We have to be in there. And then say, well, now, if we're in there, what's the probability of B happening? Well, being in here. That's where B is happening if you're already stuck being in A. But that's exactly what this formula says. It's the probability of the intersection, B intersect A or A intersect B. It's the same either way you write it, divided by the probability that you're in A in the first place. That's it. That's the whole deal. Now, there's other ways of writing this formula. Some people write it as the probability of A intersect B is equal to the probability of A multiplied by the probability of B given that A already happened, or similarly, the probability of B times the probability of A given that B already happened. So essentially, you're trying to say, if I want to find the probability of A and B, it's going to be the probability that one of them happens, and then the next one happens given that the other one already happened. And the interesting thing about these probabilities is there's kind of like three good ways of calculating them, really, depending on what information you have. Let me show you an example. So one card is drawn from a deck. So draw one card. Find the probability that it is a queen given that it is a face card. So one way to imagine this situation is I drew a card. I told you, I looked at it, I was like, it's a face card. And I'm asking you, what's the probability that this is a queen? So the nice way of doing this, I think, or the easy logical way of doing this, say, okay, well, I suppose I should try to use some good notation here instead of just making it up. So method one, we use what's called the reduced sample space. So if I say that getting a queen is event A and getting a face card is event B, then my reduced sample space is just the space of the face cards. So I'm going to call this omega B. That's my reduced sample space. Consists of, I'm so bad at drawing all these things. Consists of these 12 cards: hearts, spades, diamonds, club. The spades and the clubs are hard to draw for me anyway. And then you can have either Jack, Queen, or King for all of them. Jack, Queen, King, Jack, Queen, King, Jack, Queen, King. So what I have done is I've told you it's one of those cards. That's my reduced sample space of all the face cards. And now you say, oh, cool. Well, the probability of getting a queen, given that it's a face card here is, well, the probability of A given B is there's 4 queens out of 12 cards. That's it. You say, look at what I'm working with, and then say, how many ways of getting what I want out of what I'm reduced to working with. Alternatively, and that's 1/3, right? Alternatively, you can do this the more formulaic way. So if I want to find the probability of A given B, it's going to be, I'm just throwing the formula at it, the probability of A intersect B divided by the probability of B. Okay, A intersect B. So the overlap of face cards and queen cards are just the queens. Sometimes the overlap is just the entirety of one of them. Right here, A intersect B A is completely contained in B. So their overlap is just all of A. So the probability of getting a queen is what? 4 out of how much? 4 out of 52. So I want to be super clear. I'm not, so this is the other way of looking at it. We're not saying have a reduced sample space. We're saying probability of A intersect B without any caveats. I just said, cool, what's the probability? I'm just looking at a regular deck of cards of getting, what's the probability of getting a queen? 4 out of 52. And then divided by the probability of B, the probability of getting a face card. How many face cards are there? Right, 12 out of 52. And oh, look, the 52s cancel. So you get 4 out of 12, which is 1/3. So both formulas work. And sometimes this first way of doing it is not really an option because sometimes you're not really given like the number of things or the set of things going on, and you're just kind of given percentages to start off with. And so sometimes you're stuck using this version of the formula, but both of these are valid, and it is often easier to look for this first kind of option than the second kind of option. No, I don't like that here. Okay. I know I said there's a third way, but we'll come back to that probably next time. So let's look at a couple more examples, maybe one more example in the time we have. So, same kind of question, probability of getting a heart given that we drew a 7. Reduce sample space way. Oh, and it is good to label things here. Let's call getting a heart A and getting a 7 B. So I want to find the probability of, okay, here's a good question. Is it A then B, like A vertical line B, or is it B vertical line A? It's hard to know. So here's the thing you want to think about. The thing you are told that has happened is the thing that goes last. So we are told, or we're asked, what's the probability of getting a heart given that we drew a 7? So B is the event that we know has happened. So B is the thing that we write last. We're trying to find the probability of A knowing that B has happened. So in this case, our reduced sample space, our omega B, well, we know we drew a 7. There's 4 cards that are 7s. The 7 of hearts, the 7 of diamonds, the 7 of spades. I can pretend like I can draw a spade. Sure, no, that looks terrible. Or the 7 of clubs. Okay, that looks like a weird tree. Anyway, if those are the 4 cards you have to choose from, what's the probability that the one you draw is a heart? 1 out of 1 out of 4. One of those cards is a heart out of the 4 of them, right? Because we were told we're working with 7s only. And if we wanted the probability of getting a heart, knowing that it already was a 7, it's 1 out of 4. Or we could have done the long way and said it's the probability of A given B is equal to the probability of A and B divided by the probability of B. A and B means it's a heart and a 7. How many cards are both a heart and a 7? 1. There's only one 7 of hearts. There's only ever one suit of rank, right? There's one king of hearts, there's one queen of diamonds. There's only one each of the thing of this heart or this suit and this rank. So that's going to be 1 out of 52 divided by what's the probability of drawing a 7? And look, as usual, the things that need to cancel, cancel. Oh, there's something I wanted to say here. Oh, I know what it was. Yeah. So let me ask you a different question real quick. I know we only got a minute left, but this is important. What's the probability of drawing a heart? Which reduces to, which is the same as that. This is an example of the idea that these two events, drawing a heart and drawing a 7, are independent. It's not the same, it's not mutually exclusive, right? Their overlap isn't 0, or the empty set is technically the right word. Their overlap is non-empty. But what we're saying here is knowing that we drew a 7 didn't change the probability of getting a heart. That's the definition of events being independent. Knowing one thing has happened doesn't change the probability of the other thing happening. So here we say that A and B are independent because the probability of A is equal to the probability of A knowing that B happened. Or in other words, knowing B happened didn't change the probability of A. Didn't affect the probability of A happening. That does come up. Yeah, knowing that you drew a 7 doesn't change the probability of whether or not you drew a heart. Kind of neat. All right, that's all for today. We'll continue talking about this next week. We'll talk about some testing for disease type problems where they're like the probability that the test gives a positive result, like is 96%, et cetera, et cetera, et cetera. And yeah, they're kind of interesting questions. Oh, and I have a handout that you might find useful. Maybe that might be a lie. Nope, sorry, I only have one of them. I thought I had a whole bunch of them. I might have a handout next time if I remember to do it. It's not that great though, so thank you. And I have office hours over in CADS in the South Silo.